early days of electrical distribution, homes and buildings were often supplied with electricity from overhead lines that were more susceptible to faults and power surges. An overcurrent protection device or OCPD outside the building provided a point of disconnect and protection in case of a fault, preventing damage to the building or occupants. Also, an OCPD device outside the building made it easier to prevent unauthorized access to electricity by turning off the power from the outside. As electrical distribution systems became more reliable and standardized, the need for an outside OCPD device diminished. Several factors contributed to its removal from the requirement. Firstly, improvements in the design and construction of overhead power lines reduced the likelihood of faults and surges. Secondly, modern electrical panels and breakers provide superior protection against overcurrent and short circuits. They can be installed inside the building to protect against faults in the branch circuits. Thirdly, having an OCPD device outside the building can be inconvenient, especially in inclement weather or during maintenance. Even though an OCPD device is no longer required outside the building, the enclosure can still serve a useful purpose. Firstly, it can be used as a splice box to connect incoming service wires to the wires that feed the panel inside the building. Secondly, if desired, a disconnect switch can be installed inside the enclosure to provide a manual point of disconnect for servicing the electrical system. The original requirement for an outside OCPD device was primarily driven by safety and theft prevention concerns. As electrical distribution systems improved, the need for an outside OCPD device diminished, and it was eventually dropped from the requirements. However, the enclosure can still be useful as a junction box or disconnect switch. Electrical systems have evolved significantly over the years. Early electrical distribution relied heavily on overhead lines, which were more vulnerable to various issues. These included faults caused by weather events like storms and lightning, as well as power surges resulting from grid fluctuations. To mitigate these risks, an overcurrent protection device or OCPD was strategically placed outside the building. This external OCPD served as a critical safety measure. It acted as the first line of defense, providing a readily accessible point to disconnect the building from the electrical grid in case of emergencies. This quick disconnection capability was essential for preventing extensive damage to the building's internal electrical systems and, more importantly, protecting the occupants from potential hazards like electrical shocks and fires. In addition to safety, the presence of an external OCPD also addressed security concerns related to electricity theft. By positioning the disconnect point outside the building, it became significantly easier to control unauthorized access to the electrical supply. Utility companies or authorized personnel could quickly and efficiently cut off power to a building from the outside, deterring individuals from tampering with the electrical system or illegally drawing electricity. This aspect was particularly important in areas where electricity theft was a common issue, ensuring fair distribution and reducing losses for the utility providers. Over time, substantial advancements were made in electrical distribution technology. These improvements led to a re-evaluation of the necessity for external OCPDs. The enhanced reliability of overhead lines played a crucial role in this shift. Design and construction methods were refined, making power lines less susceptible to faults and surges. Stronger materials were used, and more robust insulation techniques were implemented, significantly reducing the risk of weather-related damage and other common causes of electrical disruptions. As the frequency and severity of faults on overhead lines decreased, the need for an external OCPD as a primary safety measure diminished. Simultaneously, significant progress was made in the development of advanced circuit protection devices. Modern electrical panels and circuit breakers offer superior protection against overcurrents and short circuits compared to their older counterparts. These advanced devices are designed to quickly detect and interrupt faulty currents, preventing damage to electrical components and minimizing the risk of fires. By installing these protective devices inside the building, it became possible to achieve a high level of safety and reliability without relying on an external OCPD. The convenience factor also played a role in the decision to remove the requirement for external OCPDs. Having an OCPD located outside the building can be problematic in various situations. Accessing the device during inclement weather, such as heavy rain or snow, can be uncomfortable and even dangerous. Similarly, performing maintenance or repairs on the external OCPD can be challenging, especially in harsh environmental conditions. By moving the primary protection devices inside the building, these inconveniences can be avoided, making it easier for homeowners and electricians to manage and maintain the electrical system. Despite the removal of the mandatory requirement for external OCPDs, the existing enclosures can still serve valuable purposes. Firstly, these enclosures can be repurposed as junction boxes. A junction box provides a safe and organized space to connect incoming service wires to the wires that feed the main electrical panel inside the building. This is particularly useful when upgrading or modifying the electrical system, as it allows for a clean and secure transition between different wiring types and sizes. By utilizing the existing enclosure as a junction box, homeowners can avoid the need to install additional boxes, saving time and money. Secondly, the external enclosure can be used to house a disconnect switch. A disconnect switch provides a manual means of disconnecting the electrical supply to the building. This can be particularly useful during electrical work or in emergency situations. By installing a disconnect switch in the existing enclosure, homeowners can easily shut off power to the entire building without having to access the main electrical panel. This can enhance safety and convenience, providing a readily accessible point of control for the electrical system. In conclusion, the original requirement for an external OCPD was primarily driven by safety and theft prevention concerns. As electrical distribution systems became more reliable and advanced circuit protection devices were developed, the need for an external OCPD diminished. While no longer mandatory, the existing enclosures can still be repurposed as junction boxes or to house disconnect switches, providing continued value and utility. Understanding the historical context and the reasons behind the changes in electrical codes can help homeowners make informed decisions about their electrical systems and ensure the safety and reliability of their homes. Electrical codes and standards are constantly evolving to reflect advancements in technology and changes in best practices. Staying informed about these changes is essential for anyone working with or maintaining electrical systems. Consulting with qualified electricians and electrical engineers can help ensure that your electrical system meets current codes and standards and provides the highest level of safety and performance. Also remember that electrical work can be dangerous and should only be performed by qualified professionals. Improperly installed or maintained electrical systems can pose serious risks, including electrical shocks, fires, and other hazards. Always prioritize safety and seek professional assistance when working with electricity. Consider the benefits of regular electrical inspections to identify potential problems and ensure that your electrical system is functioning properly. These inspections can help prevent costly repairs and ensure the safety of your home and family. Regular maintenance, such as tightening connections and replacing worn or damaged components, can also extend the life of your electrical system and improve its overall performance. The evolution of electrical systems reflects a continuous effort to improve safety, reliability, and convenience. By understanding the historical context and the reasons behind the changes in electrical codes and standards, homeowners can make informed decisions about their electrical systems and ensure that they meet their needs and provide a safe and comfortable living environment. Modern electrical panels and breakers provide superior protection because they use advanced technologies to detect and respond to overcurrents and short circuits. Firstly, electronic trip units are commonly used in modern breakers to precisely monitor current levels and trip the breaker quickly when an overcurrent is detected. These trip units can be programmed to respond to different types of overcurrents, such as overload currents and short circuit currents, providing more targeted protection. Secondly, arc fault circuit interrupters or SIs are designed to detect arc faults, which are dangerous electrical arcs that can cause fires. SIs use sophisticated algorithms to distinguish between normal arcing, such as that produced by a light switch, and dangerous arcing that indicates a fault. When an arc fault is detected, the SI quickly trips the breaker, preventing a fire. Thirdly, ground fault circuit interrupters or GFCIs are designed to protect against ground faults, which occur when current leaks to ground. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that some current is leaking to ground. The GFCI quickly trips the breaker, preventing electrical shock. Modern breakers also offer improved reliability and durability. They are typically made with high-quality materials and designed to withstand harsh environmental conditions. They also undergo rigorous testing to ensure that they meet industry standards and provide reliable protection. In addition to improved protection, modern electrical panels also offer greater convenience and flexibility. They are typically designed with more spaces for breakers, allowing for expansion of the electrical system as needed. They also offer features such as surge protection and remote monitoring, providing homeowners with greater control and awareness of their electrical system. Overall, modern electrical panels and breakers provide superior protection, reliability, and convenience compared to older systems. They use advanced technologies to detect and respond to overcurrents, short circuits, arc faults, and ground faults, preventing electrical fires and shocks. They also offer improved reliability, durability, and flexibility, making them a valuable investment for any homeowner. When considering electrical safety, it's important to know the different types of overcurrent protection devices or OCPDs. Circuit breakers are automatic devices designed to interrupt the flow of electricity in a circuit when an overcurrent or short circuit is detected. They are resettable and can be used multiple times. Fuses are one-time use devices that melt and break the circuit when an overcurrent occurs. They need to be replaced after they blow. Fuses are generally faster acting than circuit breakers, but they are less convenient because they need to be replaced. Ground fault circuit interrupters or GFCIs are designed to protect against ground faults, which occur when current leaks to ground. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that some current is leaking to ground. The GFCI quickly trips the breaker, preventing electrical shock. Arc fault circuit interrupters or SICE are designed to detect arc faults, which are dangerous electrical arcs that can cause fires. SIs use sophisticated algorithms to distinguish between normal arcing, such as that produced by a light switch, and dangerous arcing that indicates a fault. When an arc fault is detected, the SI quickly trips the breaker, preventing a fire. Surge protectors are designed to protect against voltage surges, which are sudden increases in voltage that can damage electronic devices. Surge protectors work by diverting excess voltage to ground, protecting the devices connected to the circuit. Each type of OCPD has its own advantages and disadvantages, and the best type of OCPD for a particular application depends on the specific requirements of the circuit. For example, GFCIs are required in bathrooms and kitchens to protect against electrical shock, while SIs are required in bedrooms and living rooms to protect against electrical fires. Surge protectors are recommended for protecting sensitive electronic devices, such as computers and televisions. When selecting an OCPD, it's important to choose one that is properly rated for the circuit. The rating of an OCPD is the maximum amount of current that it can safely interrupt. If an OCPD is not properly rated, it may not be able to protect the circuit from an overcurrent or short circuit. It's also important to install OCPDs properly. A properly installed OCPD may not function correctly and could pose a safety hazard. Always consult with a qualified electrician when installing or replacing OCPDs. They can help you choose the right type of OCPD for your application and ensure that it is installed properly. Regular maintenance of OCPDs is also important. Circuit breakers should be tested periodically to ensure that they are functioning properly. Fuses should be inspected regularly for signs of damage. GFCIs and SIs should be tested monthly to ensure that they are providing adequate protection. By following these safety tips, you can help protect your home and family from electrical hazards. In older electrical systems, the service entrance cable often ran directly from the meter to the main electrical panel inside the house. This meant that there was no way to disconnect the power to the entire house from the outside. In the event of a fire or other emergency, firefighters would have to enter the house to disconnect the power, which could be dangerous. The addition of an outside disconnect switch allowed firefighters to quickly and safely disconnect the power to the entire house from the outside, reducing the risk of electrical shock and preventing further damage. Also, outside disconnect switches can be useful for homeowners who need to perform electrical work on their homes. By disconnecting the power from the outside, homeowners can ensure that the electrical system is energized, reducing the risk of electrical shock. This can be especially useful for homeowners who are not familiar with electrical work. Outside disconnect switches can also be useful for homeowners who want to conserve energy. By disconnecting the power to the entire house from the outside, homeowners can prevent phantom loads from drawing power, reducing their energy consumption. Phantom loads are electrical devices that continue to draw power even when they are turned off, such as televisions, computers, and chargers. Over time, phantom loads can add up to a significant amount of energy consumption. By disconnecting the power to the entire house from the outside, homeowners can eliminate phantom loads and save money on their energy bills. An important role of a junction box is to provide a safe and convenient place to connect electrical wires. This is especially important when extending or modifying existing circuits. When connecting wires in a junction box, it is important to use the proper wiring methods. Wires should be connected using wire connectors or terminal blocks. Wire connectors are small plastic devices that twist onto the ends of wires, creating a secure connection. Terminal blocks are metal strips with screws that hold the wires in place. Wires should be properly insulated. The insulation on wires protects them from contact with other wires and metal objects, which could cause a short circuit. Wires should be properly grounded. Grounding provides a path for electricity to flow back to the source in the event of a fault, protecting people from electrical shock. Junction boxes should be properly sized for the number of wires that they contain. Overcrowded junction boxes can be a fire hazard. Junction boxes should be properly labeled. Labeling junction boxes makes it easier to identify the circuits that they contain. Another good point to know about electrical systems is to understand grounding and bonding. Grounding is the process of connecting electrical equipment to the earth. This provides a path for electricity to flow back to the source in the event of a fault, protecting people from electrical shock. Bonding is the process of connecting metal parts of an electrical system together. This creates a low impedance path for fault current to flow, which helps to trip the circuit breaker or fuse and prevent electrical shock. Grounding and bonding are essential for electrical safety. They help to protect people from electrical shock and prevent damage to electrical equipment. The National Electrical Code or NEC sets forth the requirements for grounding and bonding electrical systems. The NEC requires that all electrical equipment be properly grounded and bonded. The NEC also sets forth the requirements for the size and type of grounding and bonding conductors. Grounding and bonding should be performed by a qualified electrician. Improper grounding and bonding can be dangerous and can lead to electrical shock or fire. The main components of an electrical service entrance include the service drop or lateral, which is the overhead or underground conductors that bring electricity from the utility company to the building. The meter measures the amount of electricity used by the building. The service disconnect is a switch that can be used to disconnect the power to the entire building. The electrical panel is a metal box that contains the circuit breakers or fuses that protect the individual circuits in the building. The grounding system is a network of conductors that connects the electrical system to the earth, providing a path for fault current to flow. The size of the electrical service entrance depends on the size of the building and the amount of electricity that it is expected to use. The NEC sets forth the requirements for the size of electrical service entrances. Electrical service entrances should be installed by a qualified electrician. Improperly installed electrical service entrances can be dangerous and can lead to electrical shock or fire.